And while George is queuing up the next talk, so we'd like to make an introduction to Bill Inkle, AB4EJ, University of Alabama, and his talk title is the Personal Space Weather Station Control Software and Database. And Bill, are you online?
Bill is queued up and ready to go. His talk is ready.
Okay, and Bill, are you online?
Yes, I'm here.
Okay, great. So keep an eye in the chat window. If folks have questions for Bill, he can answer them as the presentation is going forward.
Personal space for the station network that it connects into. I'll talk about the control software and database and design and the status of all of that. Here's an overview of the presentation. First, I'll tell you briefly about what the personal space for the station network will be. And I'll talk about how the TangerineSDR will work within this network, and talk in quite some detail about how our progress is going so far. The goal of the project is to create a crowdsourced ionospheric observation system. We want to build a network of receivers that can observe the ionosphere by watching Doppler shift in WWB and other stable signals, plus other analysis as well, such as signal-to-noise ratio. This will be done at individual stations and then upload to a central host. What will this network be? Well, this network is organized by a group of universities and research facilities. We hope to have several hundred and maybe even thousands of software-defined radios scattered across the globe in shacks, schools, universities, so on. Each will include a low-cost yet powerful single-board computer with a data collection system. There are two versions of this, the TangerineSDR and the Grape ultra-low-cost version, which is being developed by Case Western Reserve University. All these will be tied together into a network for doing data analysis for science objectives, as well as we plan to let each station to be a personal propagation monitor. Here's what we'll be able to do. We believe we'll be able to do high resolution of observations of geomagnetics, the ionosphere, and other near-Earth space environment, so that we can improve our understanding of RF propagation and improve forecasting. We want to understand what happens during solar-caused radio blackouts, what to expect. We want to provide hams with their own local propagation information, and to advance scientific understanding of the ionosphere and magnetosphere. Some kinds of discoveries we think could come out of this project. We want to discover more about the causes of a range of so far poorly understood phenomena like traveling ionospheric disturbances. It seems when certain things happen, like a coronal mass ejection coming from the sun, it rings the ionosphere like a bell, creating ionospheric waves. There are other things that move the ionosphere around. It's in constant motion, such as what we call gravity waves that's caused by tides moving through the ionosphere. This is not to be confused with gravitational waves caused by collisions of black holes. This project is not studying those. There are other interesting things that occur, long delayed echoes, sporadic ionospheric movements that occur that are linked to a whole range of things. Tsunamis, upper level lows, volcanic eruptions, storms, all kinds of things that result in energy transfer between the troposphere and the ionosphere. And we hope to improve the accuracy of ionospheric models used by NASA. Let's talk about how a station actually works. If you observe the carrier frequency of WWV, you will see that it changes due to Doppler shift as the ionosphere moves around. This occurs very clearly when the sun goes up and down and when an eclipse comes through the area. The range of these movements is in the order of plus or minus 0.5 to 1.5 hertz. But you can see this clearly with a stable enough receiver and a GPS-disciplined oscillator. By using two orthogonal loop antennas, you will be able to study polarization as well. All these other things that move the ionosphere around, we'll always find these and characterize these to understand them better. Now let's talk about the network, a 20,000-foot view. The network consists of all these different systems, the tangerines and grapes, that are tied via the internet into a database system that will first run at the University of Alabama, And in further phases, we plan to make that database available other places. We're starting out studying North America, but users in other locations are also welcome, and we hope to spread this worldwide eventually. Let's talk about the logical architecture of the personal space weather system. Now, on the left, you see the Tangerine software-defined radio in that orange box. That is the Tangerine itself, including the data engine and local host, which I'll talk a little bit more about later. Some local sensors, such as a magnetometer, can also be added in order to study the magnetic environment at your location. These tie together through the internet into the space weather network. This over here is a network which will start initially at UA and then be rolled out to other locations as possible. What's in the Tangerine SDR itself? There are 2 ports for antennas, and then, well, let's talk about first the overall view. There's 2 parts, a data engine, which collects data from off the air, and then a local host, which is a small board computer used to collect that data, package it, and upload it. This data engine includes an A to D converter and a field programmable gate array to do signal processing, to do the filtering and other activities you need to do to prepare the data to upload. The data then is collected. It moves through a 3-port gigabit switch into the central, that is the local host. And the local host is tied by internet up to the central control system. Today, we're using the Odroid N2 4 GB RAM single board computer. We hope to make this work on the newest high-end version of the Raspberry Pi as well. The hardware design status, a status report on that is given by Scotty in a separate presentation, so I won't go into a whole lot of detail on this. The magnetometer has been designed and built. Version 1 is now being tested by comparison to research grade magnetometers. The data engine and radio modules for collecting the data are in final design, and also the final, the GPS-DO, the GPS disciplined oscillator for the clock is in design. Now, the software that runs on the single board computer, that's what we're looking at here. It consists of 2 parts. You see, we use a web-based user interface. That is what I call a web controller. That's written in Python. It runs Flask and Flask WT forms. We hope to make this system such that you can configure it using a user interface rather than having to go in and edit configuration files and do other engineering work on the system. Those files will be there, and you can edit them if you want by hand, but we hope to be able to do that completely through the user interface to make this thing user-friendly so that it's quite usable by schools. Now, the system, you've got a thing over here, a module called main control. That's written in C. That's in order to be able to have enough performance to handle the high-speed data coming from the data engine. That is able to decode the FT8 and whisper signals. It's able to store data to a local ring buffer, and if we plan to interface it to GNU radio. And typically the way it works is the user will click a button to turn the system on. This will pass, this web controller will pass that command to the main controller, which will then trigger the data engine to start working, and then spawn off a sub-process to do the recording, the frequency analysis, and your local propagation decoding. Data collection. We think we could be able to monitor up to 16 band segments at a time. It may be more or less than that. We have to test that to determine system capacity. We foresee 4 kinds of data collection that we're planning to support. First, the snapshotter. That's a once per minute waterfall snapshot. That's a conversion of data from time domain into frequency domain. And once per minute upshot, that is snapshot upload. That is good for cases of low internet bandwidth because this is not a great deal of data. Second option is a ring buffer. That's continuous local storage for 24 hours, then upload on request from central control. You'll be able to set a throttle on that so that it doesn't necessarily monopolize your entire internet connection if you have DSL. Then Firehose. There are two submodes of fire hose. Continuous transfer to a local supercomputer is one. Basically, in this case, the small board computer basically turns the data engine on and then gets out of the way, and the data engine just puts everything it can collect out on the data that on the network and is picked up by a local supercomputer. Another option is fire hose. This is an intermediate level of bandwidth. Fire hose to a remote server, be able to send it to your central control system with throttling is available there as well. And propagation monitoring, decoding of FT8 and Whisper on up to 8 bands each. Again, the total capacity on that is yet to be determined. Handling of collected data. As I said before, the data goes on request from the ring buffer up to your central control system. Snapshotter, same thing. You can just store this locally and play with it locally if you wish. Local propagation, we're also going to support uploading of spots to PSK Reporter and WhisperNet. And the fire hose goes either to a local supercomputer or in remote mode is throttled up to the central control system. As far as the central control system, it's very similar to the SatNOGS network. You have a data cross-reference and user account cross-reference, and then the data itself, the spectrum data, is stored as files, not as tables. The system is going to be based on Django, Celery, Rabbit, MQ, and use a Maria database as a database. Very similar to the way SatNOGS works. You're familiar with that. Here's how you'll use this network. First, you build your Tangerine system and get it working locally. We'll provide some test routines that allow you to verify that your system has been plugged together and configured correctly and is working. Then using your browser, connect to the central control system, sign up for a free account. Get a security token from the central and paste it into the Tangerine web interface. That will identify your Tangerine to the central control system. Again, this works almost identical to the way the SatNOG system works. Then you start collecting data. You can also turn on local propagation analysis at the same time. Data analysis, we're still discussing what analysis we're going to do on that, so I don't have a lot of detail to give you on what analysis we're going to do with this data. That's going to be designed in conjunction with our science partners. Here's an example of what some of this data looks like. Before I had anything working on the Tangerine prototype, I collected this data using a flex radio and use a spectrum lab. This is 4.999 megahertz. That is, we have set the radio to 4.99 megahertz, and then you have a 1 kilohertz carrier tone. You can see as the sun rises here, the frequency of WWV seems to shift, and then it's after about 15 minutes, it splits into layers, and this layer then disappears. We see a little jog here. What was that? Was that a minor solar flare? We don't know exactly what all these things are. You can very often figure out what they are by correlating this with satellite data. So that's an example. Here's a second example. I actually took this data with the prototype Tangerine running with the flex radio simulating the data engine. I'll talk a little bit more about that later. But again, you can see some things that happen. First, we see we've got this one starts in the evening. So first we see the sunset occurring where the frequency drops a bit as the ionosphere moves up. Then we see little jogs here and there. Some of these things that occur in the middle of the night, we don't understand yet what they are. Perhaps there's interaction of the ionosphere with the magnetosphere of the Earth. And then finally, you can see out here at sunrise, the D-layer absorption occurs and lose 4.999 megahertz. You see how the strength of the signal drops off. But we can still collect some good data on what's happened to the frequency. So this is just an analysis of just the frequency using FFT signal peak detection. The top is the frequency spectrum of that sample. Here is the Tangerine prototype. It consists of two parts. First of all, a simulator, which I wrote, it connects to a Flex Radio 6600 to pick up IQ data of the DAX IQ, and it simulates the Tangerine data engine. It outputs data the same way the data engine would, using original data coming from the Flex. That then is then picked up by a second system here. This consists of an Odroid N2 and a Western Digital Purple series a hard drive. The purpose of that is to use a video surveillance type of disk drive so it can survive the large number of reads and writes necessary to do the ring buffer function. The system over here, there's a couple of controls. You can start monitoring FT8, and it's got an output over here which allows you to monitor everything that is going on. It shows that FT8 is going to start in 13 seconds here. It has to start right at the top of a minute, and we can, at the same time, we can start data collection on our ring buffer, and we see we've got the hard drive flashing there. So we've got both FT8 and ring buffer running at the same time. So this is a prototype Tangerine, which is going to be developed for the software to go on the local host. Looking a little bit more closely at the software interface, the user interface for the Tangerine local host, you can see that it's a web-based system, and the idea here is that all configurations should be able to be done just using this interface, so that you don't have to do editing of configuration files. Those configuration files are there in case you do want to edit them by hand, but we want to try and avoid that. Here is where we can go and set up the number of channels we want to run and the frequencies of each. Here we can see how we can go in and set up the FT8. Whisper is still under development. I don't have anything I can display on that yet. And the idea here is that it should be possible to do all configurations and without having to do any engineering work. The system here also allows you to set throttling of upload data depending on how much upload bandwidth you have. You can also put in a number of call signs, and I'll also be adding grid squares to this so that you can get notification when a certain signal is heard, a certain that is a certain call sign or grid. Notification will go through email, which you can also configure to send you a text message in case you'd like to get a text message. You don't have to sit in the shack all the time to watch for a particular station. At least on Whisper and FT8, when they come on, you'll get a notification that they are there. We may add other features to this, but this is where it is today. So that's our user interface. So let's talk about the status. I'm not going to go into a lot of detail on this, but you see we're moving right along in making progress in getting the Tangerine working. We've got many of the modes already working, and we have FT8 decode and upload working. I'm working on Whisper right now. The design of the central control system and database is just getting started. That's being done by our computer science department. And this is something that made me very happy. I was able to run the FT8 data collector for a while and upload spots. So here you see spots collected and displayed on PSK Reporter. So that made me very happy to get that working. Finally, why would anybody participate in such a project? You can be part of new science and compete for wallpaper. The personal space weather station can provide ongoing propagation monitoring your location with multi-band FT8 and Whisper, and actually be a part of this interesting new project. So I'll throw open the board for any questions and answers, and then we'll cover those now.
Thank you so much, Bill. That's great.
I do see a question out there. Does a Tangerine use a Linux OS like the Raspberry Pi? Yes, it uses the set whatever flavor of Linux is pre-installed on the Odroid N2, which is Ubuntu, I think. Yeah. The question is, where does Grape fit into this? Well, my presentation focuses on the Tangerine. We are talking with Case Western Reserve about taking and providing a flavor of the simulator that will talk to the Grape so that you can use the same web interface to control the system, and then data from the Grape will be picked up by the simulator, pushed into the local host, and then uploaded to Central. So we hope to get those interoperable to work the same way. So let's see. The PSWS software is on GitHub, although I will have to say it's pretty immature right now. There's a lot of features that haven't yet been implemented. It still has the occasional bug here and there that I have to work out. So we're 9 months into a 3-year project, so there's still a lot I have to do. The coverage of unit testing of the software routines in the personal space weather station software has very minimal coverage right now. I hope to get unit testing to be able to cover most of the functionality of the Tangerine. But it's out there on GitHub now. But buyer beware. It's, it takes a lot of tinkering to make it work right now. Here's a question. The ring buffer can be used to record collected data locally. That capability is to be included in the final solution. Oh yeah, absolutely. The way it's supposed to work is whoever wants to participate in the project is encouraged to run a ring buffer. And we encourage you to do this on something like what I have implemented, a Western Digital Purple Series hard drive, rather than writing it to the virtual disk that's a part of the Odroid, because you will you'll actually literally wear out your solid state drive if you do this kind of read and write functionality. And the idea is that the Tangerine is going to have a heartbeat where it checks with central control every minute or two. If one of the science users had said, oh, we want to get some data. So for example, a science user, a super user, has observed there has been a solar flare or coronal mass ejection. They'll be able to put in a request. And then the next time all the Tangerines do a heartbeat, they'll get a data request from Central that gives the time frame. So for example, okay, we had a solar flare, give us the 30 minutes of data before that and the 30 minutes after a certain time so you can see what led up to it. And then the Tangerine will begin packaging and uploading that to the central host. All that's working. I've got that working and tested. I'm testing it with a virtual machine at home, so we'll have to see how well this works when you go run it across the actual public internet. So let's see, what other, are these stations expected to run 24/7? Well, that's best. If you want to be a full participant in all of this, we'd love for you to do that. I mean, there'll be a Tangerine data engine up and running, and the local host connected to your local internet. I don't know that these really draw that much electricity. I mean, anyway, I think it's best if you can have it running all the time. Let's see, what other questions do we? Does anybody else have any? I've
Yeah, hey,
tried to
Bill.
answer. You go ahead.
I have a question is, what was the data rate for the ring buffer?
The data rate for the ring buffer. Right now I'm doing that based on what the Flex Radio default speed is, 48,000 samples per second. That is a single channel, 48,000 samples per second, using IQ samples that are each the 32-bit floating point. So that simulates, we've been talking about using 8 kilohertz wide sample rates per WWV station. So 48,000 samples per second is a simulation of the data rates we'll run if we run 6 simultaneous 8 kilosample per second subchannels. And I'm able to run that. And by the way, I got Whisper working now and Whisper uploading. So right now I'm running the system with that simulated 8 kilos, in other words, 48 kilosamples per second, as well as 2 FT8 channels and 1 Whisper channel. That's all I can run with a Flex 6600 because it only supports 4 slices. If I had a 6700, I could test it with 8 slices. But anyway, I'm not trying to make the Flex the be-all and end-all of everything right now because it's just a stand-in until we have the data engine, the Tangerine hardware. What minimum local data rate is needed for uploading to UA? That is going to have to be determined. I have played around with my own AT&T DSL, and it seems to be able to upload at about 1.7 megabits. And also on the data, by the way, we're recording this data in digital RF format, which is the MIT Haystack flavor. And I found out it runs just fine if I use a compression level setting of 1, which is the minimal compression setting. But because of the nature of the data, it still cuts the data size by about 70%. So you can run a lot of data. So if I see a question about the 384 kbytes per second uncompressed. So if you take that and multiply it by 0.3, you get about what I'm running. But a lot of this is going to have to be determined experimentally. And since I don't yet have the central host software is just in first design, so I don't have the ability to upload to it yet. I can only do it with a local virtual machine that I'm running in my own local network. Expected time scale. No, what can somebody amplify the question? The expected time scale. What does that mean? If I had to shut down my Tangerine for a period, do I have to tell someone I did this? Well, the standard configuration is that the Tangerine is going to heartbeat to the central control system every minute or 2. That's configurable. It works like SatNogs. If your heartbeat goes away, we know your station is offline. And then when your heartbeat comes back, we know that you're back online. And this is a volunteer project. Just do the best you can. If you can keep it running all the time, that's fantastic. If you have to take it offline from time to time, that's expected too. Oh, when is this ready for first rollout is really the question. We're planning to have this system ready to roll out prior to I believe there's an eclipse in 2024 that somebody can Nathaniel's online. Tell me when is our rollout?
Yeah, so 2023 there's an annular solar eclipse. So we'd like to be ready for that.
Yeah.
I think one thing, so this project, it's a 3-year project that ends December 31st, 2022. So our goals for the end of that period, we have to prove to the NSF that we have a working prototype system. So that's basically what we've promised to the NSF. So basically by the end of 2022, we should have something that, you know, we can really show does something well. And I think we're well on our way to that schedule.
There's
So
a
I
question.
certainly
Go ahead.
hope to have you know, more wide scale deployment of these things before that date. But you know, that's what we absolutely have to do.
Somebody asked a question about the ring buffer. We recommend that you configure the ring buffer to save 24 hours worth of data. The system will work fine doing that. We're finding that the choke point is upload speed. Again, we're going to have to determine that experimentally, but with throttling, we hope to set it up. So, I mean, if central control asks for 2 hours worth of data and it takes 10 hours to upload that, okay, just as long as we don't request too much.
Yeah.
You
know,
we're
I
out
think
of time here, so.
Yeah, I think we can go and keep talking about some of this during the break. So why don't we turn it over to George for the break, and then you know, we can keep chatting about things once he puts up the break slide. So go ahead, George.
Oh, thank you very much. But I would much rather that Steve N7HPR took over so that I can concentrate on running as much as possible.
Oh, sure.
Steve, do you have that break slide ready, or any comments?
I do. And for everyone, we're going to segue into the break. However, you know, feel free to continue chatting.